Hello everybody and welcome back. In this video we're going to talk about a palette-based approach to outputting sprites to the screen and how we can use PNG to palette resizer and PNG to palette relative resizer to achieve our goal. So to do this, let's start by looking at what a palette is and how to create one. For doing this, we'll need to go back to the GitHub page, scroll all the way to the bottom, and I've linked this website here that lets you see all the colors that your image is made of. If you have another website or an application that lets you do this, go ahead and use that application. For now, I'm just going to look at this option because this is the one I used when I did the project. So you browse for your image, and we're going to keep looking at this Tetris option for now. Import the image, and then click on Manage this palette. This will let you see all the colors that are stored, or all the colors that your image is made of. This is important because, as you can see, so many of these colors are very similar. Honestly, I cannot distinguish the difference between these two at all. And it seems like a waste almost to have this much accuracy in this type of an image. So what would be the best option here? Well, we could use 3 different colors, and so have black, blue, and white. But that would give you very little accuracy then. So then, depending on how much accuracy you want, the scheme is to include more and more colors. So let's say that I want a little bit of accuracy, right? So what I will do is then I will include this one, and this one in my palette. So let's go ahead and do that. So to do this, we will make a list. So let's open up which one would we like? So let's just do the PNG to palette resizer. And so we will make this list in our palette_hex variable. This is what you will use anyway, so we should go ahead and use this. So to make our list. So let me get rid of what's currently stored in the list, and let's start. This first color is going to be different. I'll explain why later. For now, let's just ignore it and go back to this. So let's take that 0 hex. I'm sorry, this is going to be kind of tedious. So you can fast forward through this part of the video if you'd like. But the general idea is going to be, actually, I will fast forward for you, and I'll stop talking. So now that we've gone ahead and filled in our palette, we can see that all of the unique colors that we had on our image have been gathered here. You can see the colors are visible based on their hex values. And you can see that most of the accuracy that we needed in this image is now existing within our file. So let's go ahead and save this and go back. Now we can run the script. So let's do Python 3 PNG to palette resizer.py, and let's type in Tetris_I. So this allows us to also resize our image. The only reason this would be useful for us is if we wanted to store all of our images in one RAM and have them have the same standardized size. This way, indexing into that RAM would become very easy. If you want images that have different sizes, you can have one RAM per image so that indexing isn't a pain. And you can decide to index into which RAM you want to index into based on some state machine that you designed. So for now, I'm not going to resize because there's no real reason to, and I'll just do 20 by 20 since that was our original size, and hit enter. So now let's do this and go into the converted, because this will show us what our converted PNG looks like. Now we have this, and now let's go and open up our original one, and we have this. So as you can see, we've lost a little bit of accuracy there, right? In general, we have this same pixel here. We have the same structure to the image that we had before. And since this is a 20 by 20 image, you could lose some of this accuracy and still have the same look to the game that you wanted originally. If you add a few more colors to the palette, you can get this accuracy that you're looking for here. If you really wanted this, it's fairly the original image is fairly pixelated as is, so having a little bit of pixelation in the converted image is okay. Okay, so now that we have this, what is the real advantage? What did we gain from doing this? Well, now if we go to the sprite bytes and we open this up, we will see that now we don't have an RGB value anymore. Now we have an index into our palette. And the interesting thing about this is that now we don't need 24 bits to reference one pixel. We don't need 24 bits to tell us what color one pixel is. We can look at the size of our palette, and based on that, we can know how many bits we actually need. So we have 1, 2, 3, 4, 5, 6, 7, 8. So we're only going to need 3 bits to reference our pixels, because 2 to the 3 is 8, and if you include this final color here, then you would actually need 4 bits, but you have 1, 2, 3, 4, 5, 6, 7, 8, just making sure I didn't count incorrectly. So you have 2 to the 3, and that's it. You need 3 bits now to reference every color in your image. The more colors you add, you're going to increase the number of bits you need to index into your palette and see which color is actually needed to be output. You will do this using a color mapper on the hardware side. I think you've done this in Lab 6, so I won't really go into detail and explain how a color mapper works. You can look at the code in Lab 6 and try to understand how you can build your own color mapper based on that. So now based on this, if you have a large image, you can have the ability to only need 3 bits now per pixel. So now how is this useful to you? If, for example, in the SRAM, there's a standardized size for for one address, right? So one address can store, I think, 16 bits in SRAM. I'm not sure, but if that's the case, how is this still useful to you? Well, in on-chip memory, the advantage is that you can tell on-chip memory how many bits need to be in one address, or how many bits one address needs to address, if that makes sense. So now is when we will look at ram.sv, and I'll explain the structure. So basically what will happen here is you'll have your memory, which is just a logic, and you will basically say the number of bits per pixel. So basically the number of bits per address minus 1, and then the number of pixels minus 1, which is the number of addresses minus 1. And this basically gives you the memory that you need for one of these images. So for us, if we look at our example of this, we needed 3 bits, so we can just do 2 here, and we needed well, I don't want to really go ahead and do this calculation, but oh wait, no, that's not that too bad. So just 20 by 20, so 400, so 399. That's it. That's it. So now we have our memory that we need for this one image with the palette that we've created. Now all you need to do is put this in a folder relative to wherever this ram.sv file is stored, and write the name of the file here. So we would do Tetris underscore i.txt, and we would do sprite bytes for this. And that's it. Now this is ready to go. What happens here now is read mem h will read your hex value that's stored in Tetris underscore i.txt, and it will initialize your memory block with the values that you've provided it. And then this logic here basically allows you to write and read from the memory as you want. If you want this to be a ROM, you can get rid of this code, and you can get rid of data in, and you can get rid of write address. This basically makes it a ROM that you can never write it to. That way, you can't make a mistake even if you accidentally do. For those of you that want to use the RAM functionality and want to be able to write back into it, leave the rest of the code as is, and you can use it as you feel free. For example, you can use this code to create a frame buffer for your basically your entire game. You'll need to write the controller for the frame buffer, but this memory can serve as the buffer itself. So you can write a dual frame buffer by using 2 of these. You can do anything basically. So let's go back to the terminal. Okay, so I think that explains everything. Oh wait, no, we're still missing one thing. So if we go back to the code and go to the palette, why did we need this extra color? So to explain why this is necessary, we need to go back and look at one of the other Sprite originals, write.png. So this is a character from Contra, an old school NES game, and we can see that around the character there's a bunch of white space. This white space isn't actually white space, it's transparency, and the PNG file format accounts for transparency. But the problem is there's no real way for us to account for transparency using hardware. Because if you tell the VGA, if there was any way to tell the VGA that this pixel is transparent, what would the VGA output? The VGA wouldn't know what to output. So you have to tell it explicitly what it needs to output, the color it needs to output. And to do this, we need to store all our colors in a frame buffer and all our pixels in a frame buffer. And we need to account for the transparency by using a color that doesn't appear in the rest of the image. So for our Tetris tile, that color was red. Red didn't appear. But if we look at our new image, red does appear. So I have gone ahead and made the new palette for this. So I'm just going to copy paste it on top. If we go back into the file, we'll see that purple is that color that doesn't appear. So if we go back to this and we see, yeah, there's no purple. So now we can go ahead and run this and type in write. And I think the size is 23 by 34. It doesn't really matter. I'll resize it. So if we now go to converted and we open this up, we see that purple is now what surrounds the character. This is very useful because now when we want to output this image into our frame buffer, we will look at the pixel, we will ask ourselves, is this pixel purple? If it is purple, then instead of inputting this and putting this into the frame buffer, I will just take whatever is currently stored in the frame buffer and rewrite it into itself. This way, what this allows us to do is it allows us to output the actual character and put it into the frame buffer while keeping everything else in the frame buffer that isn't affected by the transparency as is. So that way we will have an image where the character shows up and the background stays the same without there being like a square box where the character should be. Because we only want the outline of the character to show up, correct? So this, in my opinion, is the best way to approach that problem. I hope that this was helpful. If you guys have any questions, please let me know. Other than that, I think this covers everything.